Oh. All matter in the universe is composed of charged particles. There are three primary charged particles at play. The first is the electron with a charge of -1 electron volt. The second is the up quark with a charge of 2/3 electron volts. And the third is the down quark with a charge of -1/3 electron volts. Charges are the source of electromagnetic fields. This is how a charge is felt by another charge. The charge feels the field of the other charge. It's only by fields that charges are aware of each other, are felt by other charges. A same sign charge in a field will feel a repulsion in the direction the field is moving, away from the original charge. An opposite sign charge will feel an attraction back towards the source of the charge. If we look at the field, which is created in a very small delta t, we'll find that the field moving out in all directions at the speed of light is a very thin spherical shell, because it's a very small delta t, with concentric inner and outer spheres. The volume of the sphere, which is proportional, inversely proportional to the intensity of anywhere on the shell, is proportional to the radius squared. So the strength goes down with the radius squared as the sphere grows at the speed of light. If we look at the field in a same small delta t, which is emitted by a moving charge, we'll find that it's no longer of uniform thickness. Instead, the later inner sphere is closer to the outer sphere in the forward direction. So the thickness, which is inversely proportional to the intensity, can be found according to the formula. Well, it used to be for a stationary charge, it was speed of light times delta t. And now, for a moving charge, it is speed of light minus the velocity times the cosine of the angle between the velocity vector and our location vector. So wherever we are on the shell, the angle we make with the velocity, that's the angle. And all of this is times delta t still. It's still times delta t. So we have this non-uniform thickness shell. And when cosine in the straightforward direction, where the cosine is 0, that's when the shell will be thinnest. It comes out to a thickness of speed of light minus velocity times delta t in the forward direction. This magnetic force, well, what this means is this creates a magnetic force. There is still the electrical force, but now we have an additional force which is perpendicular to the velocity of a charge moving through the field, and it is directed to wherever on the shell has the, if it's the same sign charge, it'll be directed again to the lowest intensity. If it's opposite sign charge, it would be to highest intensity. But these magnetic forces can be very, very strong because, well, it's proportional to both velocities. The field strength is a result of the velocity of the first charge, and how much field is reached is proportional to the velocity of the second charge. You know, if your charges are moving at great speed, for example, quarks can move at 99.995% of the speed of light. This means the thickness in the forward direction has been thinned to a 20,000th the field is 20,000 times as strong. A second quark moving as fast and maintaining position in such a field would have a prolonged, extremely powerful force upon it. These forces could be strong enough to bind quarks together. As well, they allow the force to reach beyond the nucleus, reach other atoms, so they can go be outside atoms, these relatively compressed fields. I will explore both of these possibilities in future videos. Thank you.